Swayam Prabha. Digital India. Educated India.
Hello, good morning. Welcome to the course on comprehensive view of speech processing, and today's lecture is 33 in sequence, and today we are going to discuss about basically I am just introducing a very important model in the context of speech processing, that is hidden Markov model. And before going to that, let us try to conclude the mixture models, that is probability density estimation, that we are trying to conclude in 5 to 10 minutes, and after that we move on to the speech, one of the another very important speech modeling technique known to be hidden Markov model. And so in the last class we are discussing about the probability density estimation using non-parametric approaches, and so there are two general approaches for estimating the probability density using non-parametric approaches, a kernel based approach, and other one is the k-nearest neighbor. And we also observed that the k-nearest neighbor can be used as a classifier as well, along with the modeling the data. And after at the end of the non-parametric approaches, we have we introduce like a KL distance as a distance measure to compute the distance between the two probability densities. So here in the context of non-parametric approaches, using a non-parametric approach, we estimate the density of the data using this either kernel based or like a k-nearest neighbor based approach, and afterwards suppose if we have a true density is available of the data, and we can able to compare the estimated density with respect to true density. That means how far the estimated density is close to the true density, that we can able to compare by using a distance measure known to be like a KL distance measure. It is a asymmetric distance measure. So where the difference between the estimated and the like a true density is weighted by the probability density, the true density and all. That means that wherever the true density is more, that means the weighting factor or the weightage will be more for the given distance and all. So that way the KL distance is introduced, and after that we introduced the semi-parametric approaches, and we already discussed about the how semi-parametric approaches are different from the parametric and non-parametric approaches. And in the semi-parametric approaches, we introduced the mixture model, where in case of semi-parametric approaches, it is neither parametric nor like a non-parametric, but at the same time in case of semi-parametric approaches, we can able to estimate the density of any complex system or any complex function. We can estimate the density very close to the true density, provided if we have a sufficient number of components and the parameters that are considered during the estimation process and all. And here in case of semi-parametric approaches, we considered one of the generic models that are used known to be mixture models. And here in case of semi-parametric approaches, any arbitrary density function we can able to estimate using some multiple number of components, where each component is modeled by using some generic function. And for example, you can use the Gaussian function or Gaussian model can be used for every component. So that way depending upon the complexity of the model, we can use a sufficient number of Gaussians. At each component, we will try to model the data using by imposing a Gaussian at that location. So that way, by using a multiple Gaussians, we can able to estimate any arbitrary density. And finally, the overall density is nothing but the linear combination of or the superposition of all these component densities gives you the overall mixture density. That is what we observed in the last class. And since it is like a combination of or a resultant of the multiple functions, so where this model, the semi-parametric model, can be represented by using again a set of parameters, where here the parameters are nothing but the parameters associated to the various components. Like for example, you have a 10 Gaussian components have been considered for modeling a given underlying data. So, for each component is represented by Gaussian. So, therefore, as it is a Gaussian, it has its parameters like a mean vector and covariance matrix and all. And likewise, for every component we have these covariance matrix as well as its mean vector, and then the resultant model is nothing but a combination of all these Gaussians. So, therefore, each Gaussian will be weighted by some mixing parameter. So, that way along with these individual component density parameters, component Gaussian parameters, we have the mixing parameters as well, that depending upon the number of components. So, all these parameters together used to represent the mixture model. So, now how do you estimate the parameters? So, for estimating the parameters here, in case of semi-parametric approaches, we use the method, the generic method as we already come across, known to be the maximizing the likelihood estimation. And so, for maximizing the likelihood estimation, we have observed here in case of semi-parametric approaches. So, the re-estimated parameters consists of the nonlinear coupled equations. So, directly solving that equations to get the optimal parameters is very difficult, it is very complex also. So, therefore, instead of using the coupled equations, what we do is that we use an iterative algorithm or iterative approach known to be the EM algorithm, that what we had discussed in the last class. So, here what we do is that initially we will estimate the parameters like the number of components and each component what are the Gaussian parameters. So, we will initialize at the beginning with some rough estimate by knowing the domain knowledge and so on, and after that we will try to iterate. That means, by using these parameters we will try to compute re-estimate the parameters of a model by observing the data. So, those parameters becomes a new parameters. With the new parameters we will try to check that whether the likelihood is maximizing or not. It is nothing but indirectly, instead of maximizing likelihood, what we observed is that we will take the negative logarithm of the reciprocal of it. It is not to be error function, we will try to minimize the error and all. So, that way we will try to each time we will try to maximize that likelihood, and every time whatever the new parameter that we computed, and using that again by using a data we will try to re-estimate the parameters. So, that way this process of the re-estimation takes place in different iterations. In each iteration we will compute a new parameters and we will try to see that whether the likelihood is maximized or not, and if it is maximized then use those parameters for estimating the parameters. So, that way in a EM algorithm it is going to be expectation maximization. It means that we will try to compute the parameters and will so that the likelihood will be maximized or nothing but the error function is minimized. And so, here is the example here that we discussed in the last class. Suppose for example, if the data that is considered is available as here in an angular region, and assuming that there are about 1000 data points over here, and all these data points are uniformly distributed in this angular region. And suppose we want to estimate the probability density of these given data. So, here using the semi-parametric approach, so just we consider there are initially the 7 components and where each component will give some random parameters like mu and mean. Here the mu is nothing but the location of the component, and the location where that gives you the approximation of mean, and the mean vector, and the diameter of this each circle indicates the spread, like nothing but the covariance related thing. Like here it is plotted in 2 dimensions. So, therefore, we simply say it is a variance and all. Otherwise, it is a multidimensional space, it is known to be covariance matrix. So, that way this is the initialization, that means at the in the first iteration at the beginning we will choose some parameters, and using those parameters by observing data using a Bayesian relations we can able to compute the parameters like a mu, sigma and the mixing parameter, and that way and use those parameters, and again we will re-estimate using the data. So, that way at each iteration we will try to see that whether the likelihood is maximized or the error function is minimized or not. So, as long as the error function is minimizing, then we will try to estimate the parameters from the data and we will refine the parameters, and then we will check the likelihood whether it is improving or not. So, as long as the likelihood is improving or error function is decreasing, we will keep on perform these iterations, and whenever the error function or error is not decreasing significantly, or there is very insignificant change in the error, then at that time we can stop the iterations, and that way at that point whatever the component parameters are there, and those are the optimal parameters. So, here in this case at the initially we will choose the 7 components and their parameters are something like this, and after 20th iteration what we observe over here is that you can able to see that there are 7 Gaussians. There are almost like arranged in a circular way as per the wherever the data is available, and almost since the data is uniformly distributed, you can also observe that the Gaussians are almost whatever at the end of a 20th iteration we have 7 Gaussians, and those 7 Gaussians are placed in a uniformly in a circular region, and all the Gaussians are almost like having the same spread, equal spread. So, that indicates that here whatever after the 20th iteration whatever the parameters we have achieved, so those are mostly resembles to the true density of the data. And here the bottom figure indicates that the curves, whatever the lines, whatever the contours here indicates that the equal probability density and all. So, that means along the contour the probability density, if you try to analyze, they are equal, and this is indicating that you can see that all these curves are encircled within the angular region. That is what the data that is given at the beginning over here and all. So, that way this is just an example, like given a data, how do we can able to like compute the parameters in case of semi-parametric approach using the mixture models and all. And so, we can also compute the parameters in the mixture model in the same EM algorithm, expectation maximization algorithm, using another approach. So, here in this approach, as you have seen in the case of the mixture models where the data is incomplete, it means that when you consider the data from a given class, right. So, that data is modeled using mixture model, and here the mixture model is nothing but there are multiple components are there, and whatever the data that we are trying to model using these multiple components, a priori we have no knowledge about like which data point corresponds to which component. So, that details are not known. So, therefore, in view of components we can consider the data to be modeled as incomplete data, and here we can able to solve this problem by considering the labels, like some arbitrary labels we consider at the beginning, right. So, therefore, xn indicates the data points where n takes 1 to n, and zi corresponds to the label or component label associated to each data point. And here the I, since there are m components, so therefore, this zi takes the m values like m components from 1 to m, right. So, this zn is the label of a mixture component associated to the data vector corresponds to x of n. So, this zn will take the values from 1 to m, one of the components. So, now by associating these labels to these data points, right, now it becomes a complete data. It becomes the complete data, but these labels are not the accurate one. These are simply some arbitrary labels. So, therefore, we can call this as the hypothetical complete data set. The initial data set is incomplete data set, but here we made this incomplete data set to the complete data set by providing the labels, some arbitrary labels. So, with that we can say that it is a hypothetical complete data set. On this complete data set we will try to estimate the likelihood. So, therefore, it is not to be E complete, it is not to be the error function for a complete data set, hypothetically complete data set. It is the same way whatever we have carried out earlier. So, this is nothing but minus log likelihood. So, not to be like minus of log of the probability of the xn comma zn, because the labels are available. Since the joint probability of this one can be written in terms of conditional probabilities like this, right. And now here we do not know about this the labels whatever we have considered is some arbitrary labels. So, therefore, we have to estimate the probability density of these labels, right, in a very appropriate way or very accurate way. So therefore, we don't know the probability density of Zn. So therefore, what we do here is that we use EM algorithm and we consider some the initial mixture parameters, right, and then use those mixture parameters and that initial parameters whatever we have. With that, we will try to estimate by using Bayes theorem, we can try to estimate the probability density of Zn. That means we need to compute the probability density of Zn by observing the data, right, by knowing a data. So we will try to adjust the probability density function of Zn, so that we will refine that in each step, right, and then we will try to compute the expectation of the error function like here. So here this is known to be E step. So here computing expectation of error function is nothing but computing expectation of likelihood. Here the goal is that, so we need to find out the new parameter values, and we have to see that at a new parameter values whether these the error that is computed or expected error that is computed, whether it is minimizing or not, right. So therefore here, so this is known to be the expectation step, and in this expectation step we have to see that whether the error is minimizing or not. It is nothing but indirectly, it is nothing but we are maximizing the likelihood or not. So that way here, by using by considering some parameters, and then we will try to estimate the mixture the mixture weights are nothing but the labels, the component labels of a data using a Bayes theorem and the new parameters, and then we will try to compute these E complete, that is nothing but error function with a complete data, and we will try to see that whether this estimated E complete from the E step, whether it is minimizing or not. So that way here also we will perform the various iterations, and each iteration will try to see that whether this error function is decreasing or not, right. And so these are the corresponding expressions for that. So computing the expectation of the error function for a complete data, it is nothing but maximizing the likelihood, right. So the M step is nothing but maximizing the likelihood. It is nothing but just when you compute that, when you see that with respect to the previous iteration whether the error is decreasing or not. It is nothing but the likelihood function or the likelihood of the given function is increasing and all. So this is nothing but further we can able to write this expression as the E complete into this one with respect to volt. And here these are the the labels can take the components the first data component, the first data the label can take any of these M values, and similarly the second the data point can take any one of these M labels with the available probability density function. So therefore you can write this summation with respect to each the label associated to each data point can take any of the M values, and then this can be simplified. Finally you can get the expression, this one, with which you can able to compute the expected error function value and all at each iteration. And this we will try to do it in each iteration, and we will compute the new parameters, and we will try to estimate the error and whether the error is decreasing or not. As long as error is decreasing, we have to keep on continue the iterations, and whenever there is not much decrement in error is observed, so at that point we can stop the iterations, and whatever the values that are available and whatever the probability density function that is associated, so that will be, by using that we can able to see the labels that are the components that are associated to various data points. And now just as we have seen so far how to estimate the probability density function, and with the probability estimated probability density function we can able to carry out the classification task, because once the probability density functions are available for every class, right, and by using the Bayes theorem, we can able to compute the posterior probability of each class, and then from that we can able to decide we can able to use that concept for the classification task, performing the classification task on the test data. And here here we have seen the various ways to estimate the probability density, functional form, and using the parametric approaches, non-parametric approaches, and semi-parametric approaches. And here I just want to illustrate that how this Gaussian mixture models can be used for performing the recognition task. So here for performing a recognition task, and here for every class, for example, that depends upon, suppose if you want to perform here the task that is here given will be isolated word recognition task. So it means that suppose for example in our home appliances, for controlling home appliances through the speech, where you can able to control by using a limited words, like for example if you want to control the fan, where you can say that switch off the fan and switch on the fan and keep the fan in 5 or something like that. With very few words you can able to control the given appliances. That depends upon whether it's a fan or a TV or whatever it is. So here in case of isolated word recognition, the number of words are finite. It may be 10 or 20, that depends upon the task, right. So therefore, for building a model or for performing isolated word recognition system, we know that the number of words that need to be recognized will be like the limited, right. So for every word we will try to we can collect the several samples or several examples of that particular word, and then from that word, from that set of, suppose for example, we want to perform isolated word recognition for a 10 word, the total number of words are 10 words. So from each word, like you can collect the samples from various people, from different speakers, and then we will collect sufficient number of samples for every word. And from each word, we will try to derive the spectral vectors, either the feature vectors in one of the techniques whatever we come across, either by using LPC analysis or MFCC or even directly the spectral coefficients or some other approaches, even time domain approaches also as well. So that way, by using one of the feature extraction technique, we can able to derive the features, and then afterwards if you want to perform in the discrete domain, so these feature vectors will be passed through the vector quantization, so that whatever the feature vectors that are derived, they are continuous in nature. So they become the discrete, that depending upon the code book size. If the code book size equals to 1024, so whatever the feature vectors that we are using for modeling the technique, it will be only 1024, right. So or otherwise 512, something like that. So therefore, we from the feature extraction module, so we will get a continuous feature vectors, and those continuous feature vectors will perform the vector quantization on it, so that we can get a coded vector or we can get the symbols and use those code vectors of a given class. Suppose in case of word 1, we have like 1000 samples or like 10,000 samples of word 1 samples are there. So from each word we will try to extract the feature vectors as per the feature extraction process. We will get several feature vectors are available and use all those feature vectors together, and then we will build the model. Here building the model is nothing but, suppose for example you have like 1 million feature vectors corresponds to word 1.